From the knowledge of the gravitational field, it is clear that the orbit of the Moon is a movement driven by two forces, the gravitational fields of the Earth and the Sun, as shown in the figure. Therefore, the original lunar orbit, which we call the base orbit, will deviate from the round shape around the Earth. So it shouldn't be that difficult to calculate the lunar orbit. To simplify, we consider that the radius of the Earth's orbit r0 around the Sun remains unchanged. That is, the Earth revolves around the Sun with the basic orbit. Assuming the Moon is in the starting position at point 1. If we consider the Earth's orbit around the Sun as a straight line, then the Earth and Moon are on the same Sun orbit with radius r0 and revolve around the Sun with the same orbital speed. When the Moon has rotated up an angle theta by the force of the Earth's gravitational field, it lands at point 2*, and the distance to the Sun has increased by a distance h. Since the Sun's gravitational field at point 2*, is smaller than point 1, the Sun-driven lunar velocity Vr will slow down a bit around it. Because the Earth also runs around the Sun at the same time, there is a difference in angular velocity between the Earth and the Moon at point 2*, around the Sun. This corresponds to a speed difference delta v between the point h, which is on the extended line from the Sun Earth and whose distance from the Earth is h, and the Moon in the horizontal direction. The component of the differential velocity delta v in the radial direction of the Earth is equal to Due to this radial outward moving speed v theta, the Moon will move from point 2* to point 2 and slowly move away from the Earth. The resulting distance L between points 2* and 2 can be calculated as follows. Solving this equation gives Let's plug the following values into this equation. These values are not chosen at random, but are determined by the following rules. Assuming that the Moon takes t1 days to go around the Earth and the Earth takes t3 days to go around the Sun, then a period of the Moon around the Earth takes t2 days. They must conform to the following equation. The masses of the Earth and the Sun and the gravitational constant are given as follows. From this, these values are determined as follows. So, substituting the following values into this equation, results in the distance at point 3 to Earth. This is the Moon's apogee. Caution, when calculating, all exponential numbers from the intermediate results must have at least one 7-digit number after the decimal point. From point 3, the horizontal speed difference delta v decreases as the angle theta increases. Also the radius r gets smaller and smaller up to 0.5, where the speed of the moon around the Earth is equal to that at the starting position 0.1. Because the moon has always moved in a radial direction from outside to inside from P3 to P5, this movement will continue after P5. So the moon is approaching the Earth on the lower part of its orbit. Why this is so will be explained physically later. The lower part of the lunar orbit cannot therefore be calculated using this equation with theta of pi to 2 pi can be calculated. It must be recalculated. So now we take 0.5 as a starting point. When the moon has rotated downwards by an angle theta by the force of the Earth's gravitational field, it approaches the Earth. The principle for calculating the lower part of the moon is the same. So the equation for the lower partial moon orbit is as follows. From this the distance at P7, the perigee of the moon is. These equations serve only as proof of how the lunar ancestry formed. It's a bit too complicated to use as the lunar orbit formula. For this we will present a very simple formula for the lunar orbit. As we can see, the calculation of the lunar orbit is not a two-body problem, nor is it a true three-body problem, because it also assumes that the Earth and Sun must rotate sufficiently. This means that they are powered by a primal force. And the previous three-body problem cannot be solved because some basic knowledge is missing in previous physics. We also see that the shape of the moon's orbit is apparently not an ellipse like the one crafted by Johannes Kepler over 400 years ago. From the above calculations it can be seen that the distances between the point furthest from the Earth and the point closest to the Earth to the base circle are approximately the same. This means that the major axis, y-axis, and the minor axis, x-axis, are also approximately the same. Therefore, the shape of the moon's orbit is not an ellipse, but rather has the contour of an eccentric. Its eccentric distance can be considered approximately as follows. To draw the orbit shape, we take two equal circles, an O, the black one, and an O*, the blue one, which are equal to the basic orbit of the moon's orbit, and place the two circles on the y-axis with a distance I between the center of O and O*. If we connect points 1 and 5, the intersection points of circle O and x-axis, with circle O** smoothly and without changing its diameter on y*axis, something like a deviated circle is created, which will be the true lunar orbit should, the red circle. And at the point O is the Earth. Thank you very much for your attention. See you next time.